In section 8.2, we want to take the central limit theorem on again, but this time we're going to take it on for proportions. So we're going to look at some new topics that we haven't seen before. Now, the first thing we want to get a handle on is what is a proportion and how does it work in this particular context. So a proportion, or a population proportion, is P, is the proportion of a population that have a certain characteristic that you're looking for. So that would be the population proportion. The sample proportion is P hat, so it has a little hat on its head. The formula for the sample proportion is X divided by N. It's the number of successes divided by the number of trials. And if that sounds familiar, that's because it's very much related to the binomial distribution that we learned about in chapter 6, in section 6.2, to be precise. So X was the number of successes, N is the sample size, the number of trials, right? All right, now what is a sampling distribution of sample proportions, and how does that work, and what does it imply? So let's suppose, and we'll just illustrate this in an example. Let's suppose we are interested in studying iPhone usage among U.S. college students. And an actual study in 2016, it was a rather large study of college students, found that 69% of college students have an iPhone. There's a link to that source. So we will assume that the population proportion is, so we assume P equals 0.69. Right? That's what we assume to be true unless we can prove it otherwise. Now, I actually did this in a face-to-face class, so bear with me. We had 19 students there that day, and of those 19 students, 15 of them had an iPhone. So this is the total number of students in the room, and this was with an iPhone. That was success. Remember, success and failure are not good or bad things. They're just what you're looking for. So we were looking for iPhones. 15 of them had an iPhone. So P hat is X over N. That's 15 over 19. Let me grab the calculator. 15 divided by 19 is 0.789. Right? All right, so that was one class on one day. So suppose we then walked around campus, went from class to class. This is obviously pre-COVID that I was thinking about this. And you poll students in everybody's class. You go one class and ask, how many of you have iPhones and how many of you are here today? And you go to the next class. How many of you are here today? How many of you have iPhones? The next class. How many of you are here? How many have iPhones? And you get a P hat for each class. You could make a distribution of those P hats from class to class to class, right? So our class would say be class number 1, and the next class over would be class number 2, and the next class over would be class number 3, and then you could build a distribution of those P hats. That is called the sampling distribution of sample proportions. It's the distribution of the P hats. Of multiple P hats, actually, from a population. Right? So we're drawing from the population of all college students in the U.S., and we're getting a P hat for each of those samples. Now, what are some things we will know? Well, the shape. The shape we want to know, but the shape is actually unknown at this point. We're not entirely certain what it will be. So at this point, we know what it will be. We know it's going to be normal, but we don't know that we have enough yet. Matter of fact, I'm positive we don't have enough with 19 of us, right? So we want to think about, we need N to be quote unquote large enough to make distribution normal. Normal is where we're shooting for, right? But we don't have it yet. So currently at this point, it's unknown. The center. The center we do know. The center is the mean of the P hats, right? What would be the center of all these different P hats from class to class to class to class? Well, the center for the P hats should be what the center is for the population, which is 0.69, right? It should be what it is for the whole population, right? The center is just the center. And then the spread is sigma p hat. Hopefully those notations are looking very familiar to you, but they're not x bars, they're p hats. Now, sigma p hat is also known as the standard error of the p hat, which has a formula. And the formula is the square root of p times 1 minus p divided by n. So in our particular case, we should be able to substitute in what p was, which was 0.69, and then say 1 minus 0.69, and divide it by n. Now notice, it's a bit different than the one for sigma sub x bar, true, but they both still have the square root of n ultimately in that denominator. That denominator is the square root here of n. And you won't have to memorize this formula either, because it's right here. We're in section 8.2, and the standard error of p hat is right there on your decision matrix that's in your exam notes packet. So we're using currently this one. In later chapter 9 and 10, we might have to approximate it with a p hat in there, but for our purposes right now, we're using p1 minus p over n. And if you remember from section 6.2, that's q. So another way we could write this is the square root of pq over n, which is actually how I wrote it over here in the central limit theorem box, which takes place in a couple pages. But you can see standard error right there, right? pq over n, right? p1 minus p. And then you can also see shape is normal, center, right? We'll only have shape normal, though, if we have some things going on up here, which we don't have yet. So we'll get there, but just so you can see how this is going to work. Now, how would I find that number with a calculator? And n for us was 19, right? Because we had a sample of size 19, which is not very large, but I just want you to see how this works. So I would take the square root button first, then 0.69 times, and now you have a choice. You can actually just write q. Q in your mind is 0.31 because together they make 1. Or you can put parentheses 1 minus 0.69, close that parentheses, then divide by 19. That will work. You can also do it with the print feature, where it's called pretty print, which is second y equals, not second y equals, sorry, alpha y equals, sorry, let me get the heck out of here. Second quit, let me get out of there. Alpha y equals, let me move over here to the right. Alpha y equals, fraction is number 1, and I choose 0.69, parentheses 1 minus 0.69. No, you do not need the times symbol in there if you don't want it, and divide by 19. Me personally, I think it's easier in Desmos, because Desmos looks always like it's going to look on the page. So if I hit square root, which again you can get from this palette down here, so square root, and then say 0.69 times 1 minus 0.69, and close that out, and then press the division symbol, and then it's going to know that, and then do 19, and you get 0.1061. Okay, one way or another, that's the spread, or that's what it's going to be if I can prove that the other aspects of the central limit theorem are met. So these pieces, in particular, this is only true if the central limit theorem is met. If it's not met, then this might not be true. Okay. All right, so this looks familiar, right? So it's just that we're looking at p hats from group to group to group rather than x bars like we were in 8.1. But the theory behind it kind of works the same. We don't know that we have a large enough sample to prove normal. Matter of fact, we don't have a large enough sample, but that would be one thing we want in order to ensure normality. And then we want the center to be the center, which in this case is p, which is 0.69. That's the assumed value for your parameter. And for the record, that's your one parameter. You'll notice there's only one parameter given to you in this problem. That is P, which is a population parameter. Population proportion. Proportion. I spelled that backwards. Which is a parameter. There's only one given here, as opposed to 8.1, which gave you mu and sigma. In proportion problems, you only need one parameter, which is P, the population proportion. All right, so that parameter right here is equal to 0.69, and then we use that parameter down here, so we really only have one single parameter given. But again, this is only true if the central limit theorem conditions are met. Matter of fact, all of this is only true if the central limit theorem conditions are met. All right, so if we want to get to that central limit theorem conditions, if we want to get to this shape center spread business, then we need to talk about these conditions. And to do that, we're going to need to play around with normality a little bit more, and we'll do that in the next example.